In this video, we are finally going to start to see how Laplace transforms might help us with differential equations. And it comes from what we're going to talk about now, which is a property of the Laplace transforms about how they deal with derivatives. And here's the rule. If the Laplace transform of a function little y is big Y, then the Laplace transform of its derivative is, and you see that all we do is we take the big Y and multiply it by the variable s. And we do have to subtract. We have to subtract little y of 0. Now that's just a number. That's the initial value of little y. Okay. Now, I'm not going to show you examples because this really is just, the way we're going to use this is when we apply it to a differential equation. Let me simply show you why it's true in this video, and then in a follow-up video we will start using this for differential equations. So let's assume we know that the Laplace transform of little y is big Y. So in other words, big Y is, of course, that integral, the definition of the Laplace transform. So now we want to look at the Laplace transform of the derivative. Well, by definition, that would be the derivative times e to the minus st dt. And actually, I'm going to just use the prime notation for derivatives for this work. Okay. Now, how are we going to work that out? And of course, we're never going to work it out because we don't know what the y is. This is a generic calculation, right? But what I want to do is I want to turn it into something that has this. Now, this is actually perfectly set up for integration by parts. Integration by parts. In a little bit of an abstract sense, but yeah, what I'm going to do is I'm going to make the u be the exponential, which normally you don't do when you're just doing regular antiderivatives, but it's going to be good here. And my v prime I'm going to make be y prime. So, right, when we do integration by parts, we take the derivative of u, that's u prime. I get minus s e to the minus st. Remember that t is our variable until we're done the integral. So minus s is just the constant that pops out. And if v prime equals y prime, well, that's kind of dumb. It's the same thing. It's like two letters meaning the same thing. V would just be y. Like if I anti-differentiate v prime and get v, I anti-differentiate y prime to get y. Okay, so if you recall, the integration by parts format says that what you get is u times v, so y of t times e to the minus st, and then that's ready for getting evaluated, 0 to infinity, minus the integral from 0 to infinity of u prime v. Now u prime is a minus, so I'll just change that sign, s e to the minus st times y of t dt. Okay, now what does this give us? Well, when we plug in infinity, y of t will do whatever it does, but as long as s is positive, this is a negative exponential. This is a decaying exponential. So when you plug in infinity, this term will go to 0. Let's assume that y of t does not go to infinity, at least not fast enough that it can beat an exponential. If it could go faster to infinity, then this exponential does go to 0. We'd have trouble. This would diverge. But that really doesn't happen in most cases, right? So let's assume that the decaying exponential wins and we get a 0. So when we plug in infinity, we get a 0. So 0. And then when we plug in 0, I get y of 0 times 1. Okay. Plus, by the way, there's the minus y of 0. That's that part. That's the second part of our rule. So we've already gotten that part. So let's see if this guy turns into the first part. And you see that it does, because s here, remember, s is just a constant as far as dt is concerned. So that can just come out. I'm just going to move that s out. And what's left is this. It's the Laplace transform of plain old little y. So that's just capital Y of s. So there it is. We got the rule. So a very ingenious use of integration by parts in sort of a generic abstract integral gives us this nice rule. And again, just to wind this up, we'll start using this in the next video. But what really makes this powerful is that differentiation is that's a calculus move. That's a calculus procedure going from y to dy dt. But we see that when you move over to Laplace transforms, what that differentiation operation corresponds to is just simply multiplying your function by s, which is a much simpler operation. Yes, also you have to subtract a constant, but that's also pretty simple, right? So we've when you sort of move from the universe of your functions to the universe of Laplace transforms, differentiation now corresponds to a much easier operation. And therefore, what you're going to see in the next video is that differential equations, when you take the Laplace transform of them, will just turn into algebraic equations. And then it'll be like we're in algebra class and we can solve those. And then, of course, in the end, what we'll have to do is we'll have to go back. And that's where an inverse Laplace transform will take place. Okay, but I'm getting ahead of myself, and I will explain that and show you examples of that in the next video. But this is the really important fact that's going to make everything work.